So you may have noticed I did it again in the previous example. I mentioned that H was a two-dimensional subspace living inside of R3. Well, what does that mean exactly, that H is two-dimensional? Now we're going to actually clarify that. So we're going to start with a fact, though, and here's the observation. If you have any subspace of Rn and you have two bases for the same subspace, so say you've got a subspace H and you've also got a basis B1 and then another basis B2. Okay, so the vectors in B1 and the vectors in B2 might look drastically different. They might look nothing alike, and their orientation might be totally different, but the number of vectors in each of the two sets has to be the same. That's a law, which is pretty neat. Let's look at an example of when we've actually witnessed that without maybe commenting on it. Consider R3. What's a basis for R3? Well, the simplest one would be the standard basis. In fact, the vectors are right here, E1, E2, and E3. That's the standard basis for R3. It contains three vectors. Another basis for R3 we talked about in this example. The basis consisting of these three vectors, V1, V2, and V3. So notice that there's three vectors again in both cases. The number of vectors in both of those bases is equal to 3. And in fact, if you were to go find any basis for R3 and then come to me and say, hey Kyle, I found another basis for R3, do you want to see? I'd say, sure, yeah, show me. But I know without even looking, I know in advance that that basis is going to have three vectors. And if you show me a basis that has 4 vectors or 2 vectors or anything other than 3, for the number of vectors, right away I'm going to want to take a closer look at your work, because I'm going to say something can't be right there. And that's because of this law. Okay, so if you have a subspace of Rn and any two bases for that subspace, both of your bases are going to have the same number of vectors. And because of that fact, that's what makes this next definition make sense. Okay, so we can finally define now the dimension of a subspace of Rn. So take any subspace of Rn, call it H, and now we can talk about the dimension of H. And the notation that we use is this dim, short for dimension, and then put H in brackets afterwards. So, and what is the dimension? It's just the number of vectors in any basis. And it doesn't matter which basis you pick because they all have the same number of vectors, right? So in general, your workflow would be as follows. If I give you a subspace and I don't tell you anything else about it, but I ask you for its dimension, then your first job is to figure out what a basis is for it. Figure out some basis and then just count the vectors in your basis. Okay, so let's take a look at a couple of examples that we've actually looked at before, but let's see how comments that we've made in the past actually fit in with this definition. Okay, so here's a line in R3 in this picture, okay? And the line has a direction vector of v. Remember, if you draw a vector as a position vector in R3 starting from the origin, and you now stretch it out and consider all the multiples of it, all the positive multiples and all the negative multiples, well, algebraically what that is the span of that vector. But geometrically what it is you end up getting a line in R3. And I've casually referred to lines as one-dimensional objects in the past, but here's why. Because that direction vector, that one vector that you have, that's going to be, that single vector will form a basis for it. So you have to start with the assumption that it's a non-zero vector, otherwise you won't get a line when you take all the multiples. But that's the idea, okay? So if you've got a line written as the span of a single non-zero vector, let's write out some details. In this case, B, which is just going to be a set containing that one vector V, is a basis for the line L. So the name of the subspace in this case was L. So because of that, you can say that the dimension of L is equal to 1. Okay, so lines are one-dimensional, figuratively, but also precisely in terms of the definition that we just introduced. Okay, what about planes? I've often referred to planes as two-dimensional subspaces, and the example on the previous page was an example of that. So why is that the case? Why are they two-dimensional? Well, remember how you get a plane? You take all the linear combinations of two non-zero vectors where neither of the two vectors are multiples of the other. Under those circumstances, if you take all the linear combinations of those two vectors, you're going to generate a plane in R3. So Well, if that's the case, then those two non-zero vectors that you started with, by the way, saying two non-zero vectors that are neither of which are a multiple of the other, that's the same as just saying let's take two vectors that are linearly independent. Okay, so if you take those two vectors and then you let H, say, be the span of those two vectors, it's a set of all linear combinations, you're going to get this plane, and guess what? You've also got a basis for that plane. So I'll say B, the set containing the vectors U and V, is a basis for H. So in this case, the dimension of H is equal to 2. So planes are two-dimensional. So now you know why they're two-dimensional. A couple other comments. Remember that Rn, the concept of dimension applies to any subspace of Rn. Well, what if you take all of Rn? That's also a subspace, so you should be able to talk about its dimension. And in fact, it's going to be exactly what you expect, right? The dimension of R3, we even casually have called it three-dimensional space all along. Well, guess what its dimension is? 3. It's because it's three-dimensional, right? So this definition is a good definition in the sense that that's what you would expect it to be, right? So if you take R3, its dimension is going to be 3. If you take R4, its dimension is going to be 4. R2, dimension is going to be 2. And for any integer n greater than or equal to 1, the dimension of Rn is always going to be equal to n. Okay, and the trivial subspace. Remember, that's the subspace of Rn consisting of only a single vector, which happens to be the 0 vector. If you give it some thought and you play around with it, the conclusion that you'll find is that there is no way to come up with a basis for the trivial subspace, right? The only spanning set you could ever write down for the trivial subspace is just the set containing only the 0 vector. But the set containing only the 0 vector is not linearly independent. So for that reason, you'll never be able to come up with a basis for the trivial subspace. So for that reason, we just say that it's 0-dimensional. Okay, so for the trivial subspace, we just define the dimension to be 0, because that's the only thing that makes sense in that circumstance.